Hi, good evening, everyone. Sorry, I got a bit late today due to some unforeseen delays. So sorry about that, and thanks for hanging around. I will just share my screen and we can start right away. Yeah, hi. I hope my screen is visible. I'll just share my screen. So the presentation that I made isn't it backed up, so I was just waiting for it to get backed up. So within that time, we'll just see a recap of whatever we went through in this week. And then by that time, the PPT would have been backed up. And from that moment, we will start the problems. Okay. So yeah, so in this week, you studied about the drive circuits for BJTs and MOSFETs. So apart from the driving mechanisms, you also went through the overcurrent protection as well as the snubber protection, right? So just hang on a second. I'll just check if it is backed up. Yeah, so thank you guys for hanging around. I'll just start now. Actually, the PPT didn't get backed up initially, so I wanted someone else's help to get it backed up. So yeah, thanks for hanging around once again. Okay, so I hope my screen is visible and I hope I'm audible as well. So I'll just start now. Welcome again to this week 11 of problem solving session for fundamentals of power electronics. Yeah, so we'll jump right ahead into the problems, right? And I think there are a lot of problems over here. So going through them itself will be a quick recap of this week. Okay, so without much further ado, let me start. The first problem is the gate driver circuit has the following parameters. That is VCC is 20, right? I'll just turn on my laser. Yeah, so VCC is 20. The peak magnetizing current is 5 amperes. You can understand it's in the primary side. The forward voltage drop DF is 0.7 volt. What can be the minimum collector to emitter voltage rating of Q1 if RF is 50 ohms? So you can understand that there is this. This is basically what? This is which converter over here? Can anyone tell? Or which kind of a drive are we having over here?
A forward converter.
Correct. Fine. So we have a forward converter and Q1 is being driven by this two resistor basic drive, right? So the drive is basically R3 and R4 and you have a potential divider kind of an arrangement and you give the VB over here. It's obviously an NPN transistor. So if your VB is high, the Q1 is going to get turned on and that would obviously be the duty period or the DTS period for the converter. Correct? Okay. So anyway, the idea is your VCC is 20, the peak magnetizing current is 5 amperes, right? So what can be the minimum collector emitter voltage rating if RF is 50 ohms? So your RF is given, you just need to calculate what is the blocking voltage for Q1. Okay. So how do we do that? So just apply KVL in this loop. Okay. That is when your Q1 is going to be turned off, right? So then what would be the voltage that is going to appear across the collector to emitter? So obviously seeing this circuit, you understand that the emitter is towards the ground side, right? So your VE potential is 0. You just need to compute what is VC, right? And when your Q1 is turned off, so obviously this magnetizing inductance would be kind of freewheeling through the demagnetizing shunt branch, right? So then what would happen? What would be the path? Your path would be something like, if I have to draw it, it would be something like from VCC, then through DF, RF, and we get over here, we come over here, right? So just apply KVL over here. So that is why you would be getting something like VCC, and then you have minus VDF, right? And then you need to add up the IFRF component. Okay. So the same has been done over here. That is your VCC is 20. And then your VDF is obviously 0.7 volts. And they have given the magnetizing current, or I mean the demagnetizing current to be 5 amperes multiplied by 50 ohms. Right. So just it's a direct KVL relation. So um, let me take my,
Sir,
yeah.
sir, what is
Hello.
the polarity?
Yeah, sure. So the polarity is something like this. Okay, so you have the plus over here. Just a second. So this is what? This is your 20 volts. Okay, and then this is what you want to find out. We call this as VCEQ1. Okay, so you have the plus over here, right? And then you try to understand what would be the peak magnetizing current is 5 amperes. Okay, so when the switch is off, right? When the switch is off, so what would happen? Your inductor is kind of freewheeling something like this. Okay, your inductor is kind of revealing something like this. So you obviously do know that you have plus minus something like this. So similarly, there will be plus minus something like this. So if you write KVL, what do you get? VCC plus VDF plus IFRF, correct? So that is why you get 20 plus 0.7 plus whatever is the IFRF, right? So 5 into 50. Yeah. So that's why you end up with 270.7, right? So obviously you need to find out VCE. So consider the device to be in the offset and then you proceed, you get the answer, right? Okay. So if this is fine, we will move ahead with the next question. So the next question is something like this. The speed up based drive circuit has the following details, right? So VBEQ1, VBEQ2 are 0.7 volts. VC is at for Q2 and Q3 is 0.2 volts, and IC1 is 1 ampere, VCC 15, VH is 20. Okay, so we'll just see what's the circuit and then we'll come back to this. So the question is, what is R1? Okay, so this is the circuit that's shown over here. And can someone tell what is this circuit? So what
The
is this
totem pole.
particular? Yeah, so this particular configuration of Q2 and Q3, something like this. This is called the totem pole configuration. And of course, you would have learned from the lectures that both the operation of Q2 and Q3 is actually mutually exclusive, right? That is, you have a high over here, only Q2 will turn on. And when you have a low, only Q3 will turn on. So they are mutually exclusive. You don't have the hazard of a short circuit across VCC. Okay. So that is an advantage that you get with our totem pole configuration, right? So you have the totem pole over here, and this is being driven by what? This is being driven by a PNP transistor, which in turn is being driven by a two resistor kind of a resistive divider basic gate drive. So VG is your input over here. You can understand that if your VG is low, let me call it low and high. If your VG is low, obviously your Q4 would be turned on. So if your Q4 is high, then what would happen? There would be a high over here. So your Q2 will be turned on. And when your VG is high, then what's going to happen? Your VG is high, therefore your Q4 would be off. So obviously your Q3 is going to be turned on, right? Okay, so this is the operation. Here we need to find out in this problem what is R1. Okay, all others are given. Okay, so
Tell me that.
sorry?
What is does more positive than mean?
Sorry, your voice is very stifled. I'm not able to hear you. Can you come again?
Yes. Sir, in the lecture, it has said that more positive than something relate to it. Can you something explain it?
More. Uh, can you type it in the chat box? Actually, I'm not able to hear you properly. You can type it in the chat box. Okay, so I will take the questions like when we have a break between questions. Okay, so I will try to answer those questions during that time. Right. For now, let me go ahead. Probably I will turn off my
Okay,
video.
sir.
So probably there is some bandwidth issue, and that's why I'm not able to hear properly. Okay, so yeah. Okay, so I'll go through this question. So for the circuit that was shown, all these are given and you are asked to find out what is the value for V1 and for R1. Okay, so you first try to understand when R1 will come into play. Okay, that is, you can understand that. So seeing this circuit, right? So when is R1 going to come into play? So is it during the turn off to turn on transition, or is it during the total on period, or is it during on to off transition, or what? So during which period will R1 come into play? Okay, so you can understand that the idea is you have the speed up circuit over here. Right? So, okay, so you have the speed up circuit over here. The idea is you want to have a high surge current during turn on, during the process of turn on. So during that period, what you would want is your current should be going through this R2 and C branch. Okay, because this is an uncharged capacitor which acts as a short circuit, and typically you will be having R2 is equal to R1 over 5. It will be at least 5 times lesser generally, typically. So in that scenario, obviously this highlighted branch in green would be the lesser impedance part, so more current would be flowing through this. And once the device turns on, or once the capacitor gets charged up, then what would happen? If the capacitor is charged up, then a charged up capacitor basically acts like a open circuit, right? So it's now an open circuit after the capacitor gets charged up. So the rest of the current, when the device is completely turned on, it would be flowing through R1. So you can understand that R1 is during when the device is completely turned on. Okay. Okay. So with this information, let's try to calculate. Okay. So you see what's written over here. That is from basic principles, you know that, see, what is the voltage across R1? So this voltage and this voltage over here, correct? So what would be the voltage that appears over here at this node? So at this node, the voltage would be VCC, that is this VCC, and then minus whatever is the VCE sat of Q2, correct? So this would be the voltage over here, right? And what would be the voltage over here with respect to ground? It would just be VBE Q1. So this would be VBE Q1. So what is the voltage across R1? This minus this, right? That is VCC minus VCE at Q2 minus VBE Q1, right? So this would be the voltage across R1. And how do you rate R1? R1 would be rated for the maximum on current, or IB on Q1, correct? So you would have learned that for driving the BJT, you have the IB plus, correct? That is the surge current that you need. So let's say we were at 0. Yeah. So let's say the base current was 0 initially, and then you wanted to turn Q1 on. So you will make your base current go to a very high value, or the surge current, so that you turn on quickly, and then it will come and settle to a steady state value. Correct? And when you want to turn it off, you will make it go sufficiently negative to remove the charge carriers, and then you will make it back to 0. Okay, so this is the profile that you typically follow, right? So this is IB plus, correct? This is your IB plus. This will be IB on, and this will be IB minus. So just now we established that R1 will be coming into play during which period of time? R1 will be coming into play when your device is completely turned on. So this is off period, correct? This is completely on period, and this is the off to on transition. Okay, this is your on to off transition, and the cycle repeats. So you understand that your R1 is going to come into play when your device is completely turned on, okay, during this particular period. Okay, because during this transition of off to on, you have R2C1 branch coming into play. Why? Because during that period of time, This C is completely discharged. Therefore, the completely discharged capacitor acts as a short circuit. Inherently, you will be having R2 as R2 is at least 5 times lesser than R1. Okay, R2 is at least 5 times lesser than R1, right? Um, so when the device is turning on, there would be a low impedance path through R2C, and that is your IB plus, that is your surge current or maximum current. And then when the device is completely turned on, what would happen? This capacitor would have charged up to VCC, right? This capacitor would have charged up to VCC minus VCE at Q2. So a charged capacitor acts as an open circuit, so there is no path through R2C when the device is completely turned on, right? There is no path. So in that scenario, only R1 provides a path. So current through R1 is only during when the device is completely turned on. So that is why here we have divided it by IB on Q1. Okay, not IB plus, it is IB on. I hope you get the point. So you just need to compute what is IB on, correct? So how do you compute IB on? IB on is basically 2 into IC by beta, correct? That is your IB on. So beta is HFE sat anyway. So 2 into IC is given in the problem as 1 ampere and beta is also given as 10. So you get 0.2 amperes. Correct. So this is your IB on. So you just plug it in over here, you get what is R1. Okay. Let me erase the unnecessary parts. Okay. I hope you understood this particular problem. That is, R1 is being asked over here, right? And the first thing you need to identify is, okay, if some element value is asked, when does it come into play, right? So when does it come into conduction? Okay. So R1 comes into conduction when the device is completely turned on. When Q1 is fully on. Okay. And R2C will come into conduction when Q1, oh, when Q1 goes from off to on transition. That is a turn on transition, and this will happen when Q1 is fully on. Okay. Right. So with that knowledge, if you know that, then what would be the answer for R1? R1 would be this voltage minus this voltage divided by the current. Okay. The current is IB on because it comes into play when it is fully turned on. You know this voltage is VCC minus VC is at Q2, and the voltage over here is simply VB Q1. Okay. And then the current is going to be IB on. IB on is basically 2 into IC by beta for Q1. Okay. Simple, right? That is 2 into IC1 by HF is at Q1. Okay. Referring to the previous question, the value of C is what? Now you come to the next part. That is, what is, oh, I don't know. It has appeared over here. Okay. So what is the value for C? Right? That is the question. So what is the value for C? So you understand that we just saw that R2C will come into conduction only during turn off to turn on transition, right? During that period only, this is going to come into conduction. Let's see how do we solve that. Okay. Right. So first of all, for any RC circuit, you know that the time constant is basically tau is equal to RC, right? And in this case, it is R2 into C. That is one expression, right? And the second expression was, you can go back to the question over here, right? They have given turn off time for Q1 focus at point number 4. The turn-off time for Q1 is 100 microsecond, which is 5 times the R2C time constant. Correct? So 5 into R2C, right, is equal to what? 100 microseconds. Okay. Therefore, you can reduce that R2C is basically 20 microseconds. Okay. So this is the first relation that we have got. And secondly, they have also told that, look at point number 5. R1 is 5 times R2. Okay, R1 is 5 times R2, or R2 is R1 over 5. Right, R2 is R1 over 5. We just computed what is R1 in the previous problem. So you know what is R2. If you know R2, you know what is C. Okay. So yeah. So as I was telling, 5 times 5 tau is equal to 100. So from that you get that R2 into C is 20 microseconds. And they have also given that R2 is equal to R1 by 5, right? That is, we just got R1 as 70.5 ohms. So R2 is equal to R1 over 5. So you get what is R2. If you get what is R2, you get what is C. Okay. So this is 1.42 microfarads, right? Okay, so this is one set of problems. So wherein you needed to compute what is R1, and you have also computed what is R2 and what is C using the data given. So for computing R1, what did you do? For computing R1, you just saw what was the voltage over here. You knew that R1 is going to come into conduction when the device is completely turned on. So the current is going to be IB on. So this IB on is basically 2 into IC by beta, correct? So that is your IB on. So based on that, you compute what is R1. Secondly, they have also given the turn off time, which is 100 microseconds, or 5 tau is 100 microseconds. So based on that, you also know that R2 is equal to R1 over 5, which is also given in the problem. So you compute what is C. Simple, right? So this is one kind of a problem. Okay. Okay. So the next problem is, the inductive turn off base drive circuit details are given below. What is the value of L required to speed up the turn off transient? Okay. Okay. So what is the value for L that is required is the question. Okay. So again, you just need to apply KVL in this loop. Okay. See what we have done over here. That is L dIL by dt. If you take the polarity something like this, then it would be. So again, you need to identify what, under what condition this L is going to come into play. They have already given that it's a turn off base drive circuit. From the lectures also you can understand that. So obviously the current is going to be what? The current would be IB minus, right? So you have IB plus and then IB on and then IB minus. So IB plus is for when for the transition from off to on, you use IB plus, and when the device is fully turned on, you use IB on, and when for the transition from on to off, you use IB minus. Correct? So with that information, you know that LDI dt is equal to what? IB minus into R2, correct? Minus VBE of QP, correct? So basically this is just a KVL over here, and you know that again IB minus would be what? IB minus is basically 1.5 times. It is generally kept as 1.5 times IB on. Okay, so 1.5 times into 2 IC by beta, right? Yeah. Again, they have also given the problem that IB minus is 1.5 into 2 into IC by HFE set. Or as a rule of thumb, also generally, we take IB minus as 1.5 times IB. So with that information, you just need to substitute the given values over here. So you get 4.55 volts, that is your LDI by dt, right? So L di over dt is 4.55 volts. Therefore, L is basically 4.55 over di over dt. So this is not 1.05, this is 4.55. Okay, right. So again, this is a simple problem. You just need to apply KVL in this loop. Okay, just apply KVL in this loop. Okay. Uh, Sundaresan KR, can you please unmute yourself? Okay, thanks very much. Okay, so this was just a KVL problem, right? So we will move ahead with the next question, which is a question based on overcurrent protection, right? So a MOSFET gate driver with overcurrent protection is used, wherein Vref is 1.5 volts. That is, this particular voltage is 1.5 volts. At what current ID in amperes will the protection get activated to switch off the gate drive? So your V diode is 0.6 volt, correct? So this is 0.6 volt. So for what ID will my overcurrent protection get activated, right? Or for what current will my overcurrent protection get activated? Okay, so you understand that this is a comparator, okay? So the output of comparator will go high when it will go high when V plus exceeds or V minus. When V plus is just above V minus, it would go high, right? Therefore, you understand that what is V plus? V plus is connected over here, right? Correct. So V plus is connected over here. So um, you know that this can be approximated as a resistance, right? So this entire MOSFET can be approximated as a resistance when the MOSFET is in the ohmic region, right? When the MOSFET is in the ohmic region, you can approximate the MOSFET as a resistance called RD or RDS on, right? That is your drain to source resistance. And in that case, what would be the voltage over here? The voltage over here would be VD naught plus IDRD. So VD naught plus IDRD would be V plus, and that should be more than Vref, correct? So VD naught plus IDRD minus Vref should be more than or equal to 0. Okay. So you know the parameters, that is VD naught is given as 0.6 volt. Okay. ID is what you need to find out, and RT is given as 0.85 minus Vref, okay, should be more than 0. Therefore, ID you can get by solving this inequality. Okay, fine. Okay. Yeah, so one point was in this problem they have not specified the 0.85 resistance, I guess. Yeah, so one more thing is RD is equal to 0.85. It was not specified in the problem. Okay, RD is 0.85 ohms. Simple, right? Just look at this comparator and apply the inequality, you get the answer. Okay, V plus should be more than V minus, and that's the idea. Okay. So referring to the above question, RBCB is used between A and B point to provide blanking time during starting each gate pulse cycle. Right. So look at here, look at this region. You have RB and CB. So what value of capacitance CB is used to provide blanking time of 1 microsecond when RB is 1 kilo ohm? So RB is given. What is your CB so that the blanking time is 1 microsecond? Okay, so you need not know power electronics to solve this basically. So just you know that time constant is tau is equal to RC, and you know the RC is given as 1 micro. So 1 micro is basically what? 1K into C. Therefore, your C turns out to be 1 nanofarad. Simple, right? It's a very, very simple problem. That is, blanking time is asked and blanking time is given, capacitor is asked. So your RB is also given. So you just substitute that over here. But apart from that, why do we need a blanking time? Can anyone answer this? Why at all a blanking time is required, necessary? Why is it necessary? So why is a blanking time necessary? So why is a blanking time necessary? Anyone? So you can understand that if this blanking time was not there, then what would have happened is when the device is turned off, right? So when the device is turned on, it would be obviously blocking a huge voltage, right? So in that scenario also V plus is more than V minus, okay, when device is off. Okay. Okay, so this is one scenario. Second scenario is when the device is turning on, right? That is, you have given pulses over here. So when the device is turning on from off to on transition, what happens is your voltage, right? VDS will slowly fall. So that time also VDS would be very high. Okay, VDS is falling from a high value to a low value. So during that time, right, when VDS is falling, it would take somewhere around a few tens or even hundreds of nanoseconds. So during that time also your V plus would be more than V minus, okay, during this off to on transition. So V plus would be more than V minus during this transition. Therefore, again, it would lead to a false triggering. Okay, it would lead to a false overcurrent thing, and immediately the pulses would be turned off. You don't want that to happen, right? You don't want your overcurrent protection to operate when you're transitioning from off to on period. Okay, because during that time your VDS is falling, so you need to provide some time so that your circuit doesn't operate during this transition, and that is why you provide a blanking time. That is, it is sometime you provide so that even at the start of your pulse, you ensure that this overcurrent protection doesn't false trigger, right? So that is why you provide the blanking time, and of course you understand that this blanking time is kind of controllable if you control what is RB and CB. Okay. Yeah. So that was about that. Let's go on to the next question. So this is about snubbers. Okay. A coupled inductor in series with a MOSFET operating at 80 kilohertz with duty ratio varying from zero point 0.3 to zero point 0.7, right? So an RCD turn-off snubber is connected in parallel to the switch. You can observe here, there is an RCD snubber. So the input supply to the converter is 48 volts and the average inductor current is 65 amperes. So anyway, the inductor is in the other side, in this output side. So it is 65 amperes. It can be kind of like a forward converter or a feedback converter or even a kind of a push-pull configuration. So this number capacitance required if the maximum turn-off time is 60 nanoseconds, this dash. So what is this number capacitance, right? Your turn-off time is given as 60 nanoseconds, okay? And your input is 48 volts, right? The duty ratio is of course varying. The frequency, switching frequency is 80 kilohertz, okay? So what is this number capacitance is your question, right? So you would have learned from the design of snubber capacitors, right, that your C is basically what? C is equal to IL into TF divided by 2 into VCC, correct? So it's a direct substitution, okay? So you would have learned about shunt numbers and series numbers. You would have learned that um, for a shunt number, the C is something like this. That is your IL into TF by 2 into VCC. Or in case of a series number, you would have learned series is directly a dual, right? So VCC into TR, TR divided by 2 into IL. Anyway, so just substituting the values over here, you will get what is the value of C. Okay, that is IL is given as 65 amperes. That is your IL, right? And your VCC is nothing but 48 volts. That is your VIN. Okay, and TF is also given. TF is given as 60 nanoseconds. Okay, so from that you can compute what is C. It's a direct relation, I guess. Okay. Okay. So referring to the previous question, so you have found out what is C, that is IL into TF by 2 VCC, 40 nanofarad. So what would be the value for R? So what is the value of R? Is the question, right? So again, computation of R was also something that you went through. That is, you learned that there is a minimum to maximum limit in R, right? So that is, you need to have maximum value. The maximum limit is being set by the time constant. That is, you want it to settle within that time, right? So R should be less than T on minimal by phi C, or you tell that phi tau, right? Phi tau should be less than, the settling time should be less than your T on minimal. So this defines your minimal time. Okay. So you can understand by substituting over here that T on minimal would be something like this, right? That is 0.3 into 1 by 80k. Why is it 0.3 into 1 by 80k? So your T on minimal is computed by your duty ratio. So duty is varying from 0.3 to 0.7. Okay. And you're operating at 80 kilohertz. Fs is equal to 80k. Therefore, your T is equal to what? 1 by 80k. Okay, that's your total time period. So what will be the on time? Minimum on time. Minimum on time is going to be the minimum duty, 0.3 into what is the time. Okay, so that is why we have done T on minimum is equal to what? T on minimum is minimum duty, right? D minimum into 1 by T. Sorry, D minimum into 1 by F. D minimum into T or D minimum into 1 by F. So that gives you T on minimal, and from that you compute what is R. Okay, that is based on this relation that we just wrote. Phi tau should be less than what? T on minimum. So remember that it's a minimum value. So you need to consider the minimum value of duty. Okay. Okay, so you just substitute that over here, and you get T on minimal as 3.75 microseconds, and you computed what is the value of C, that is 40.625 nanofarad. So you just substitute that over here, you will get the answer. Okay. Okay, so this was regarding this number design, and finally you just need to compute the power rating for the resistance. So power rating is computed based on the energy it needs to dissipate, right? So it would be dissipating this half CV square energy in every switching interval. So half CV square into Fs, right? So energy into frequency gives you power. Okay, energy into frequency will give you the power. Okay, so that's what you do over here. So half into C, VCC, and Fs, you can directly get what is the power rating. So half CV square into Fs. So the power, you can call it as I square RT, correct? I square R, where you need to take this as the IRMS, right? This is your IRMS, but obviously the simplest way would be you would take because the resistor is just going to dissipate the amount of energy expended over here, that is in the capacitor, so it would be half CV square into the frequency, switching frequency. Okay. So in this number, we have seen three problems. That is how to calculate your C first of all, correct? And you saw that this was something standard. That is, you know that the formula is something like IL into TF by 2 VCC, right? I'm not going to the derivation, but yeah, you just with the boundary conditions, you saw how to derive C is equal to IL into TF by 2 VCC. So that was your first problem. Second problem is how do you calculate R? You know that R can be calculated with the minimal or R is within the limit, right? That you would have learned in the lecture slides once again. That is, it needs to settle within the minimal on duration. Okay. So you take the duty, minimal duty, that is the minimum into T, that would be T on min. So phi tau should be less than T on min. So you get what is R from that relation. You already know what is C, and from that you get what is R. And now that you have got R, you can get what is the power rating, that is half CV square into Fs. Okay. So till this point, is there any doubt? Yeah, so I have to take that one question. So charged capacitor as, yeah, of course, charged capacitor is open circuit, so that's why you don't consider that. And more positive than in totem pole. Okay, yeah, so in totem pole, where servo telling the more positive thing was over here. Where were we? Yeah. So the point was this, right? That is, um, when would NPN turn on? NPN would turn on if your VBE is positive or VB is more positive than VE. And when would a PNP turn on? PNP would turn on when your VBE is negative, or what? If your VE is more positive than VB, right? That is your emitter terminal is more positive than your base terminal. So this is your emitter terminal E3 and this is your B3. If your E3 potential is more than B3 potential, then your Q3 will turn on, right? So when your E3 terminal will be more positive than V3 terminal, then only Q3 will turn on. So that is the meaning of more positive or more negative. Okay. Okay. So till this point, if there are no more doubts, I'll just please give me a break for 2 minutes. I'll just drink some water and then we will continue from question number 10. Okay. So Yeah, so we'll just start off from that point. Okay. Okay, so the next question is a converter switch gets driven by a gate driver circuit as shown in the figure below with the following specification. VDC is 48 volt, RL 50 ohms, MOSFET switch is given, VC set is given. By considering the maximum turn on time, calculate the value of the gate resistance RG. Okay, so this is again, as you can understand, this is a totem pole configuration, right, of Q2 and Q3. You again have NPN and PNP in cascade, and it's being driven by a PNP transistor Q1, which has a simple two resistor base drive. Okay. So the question is, okay, so VDC is given 48 volts, RL is also given, the switch is given, so obviously we need to refer to the data sheet, and the VC that is also given for Q1, Q2 and Q3. Okay. So the turn on time is given as 1 microsecond. So what is the value for RG? Okay. So again, you can understand that IG plus is basically what? So the IG plus that is required to go over here, that would be basically 2 into QG by T on, correct? So dimensionally also you can understand that the charge by time equals the current. So you require at least twice the current that's required for turning on the device. So from the data sheet, you understand that QG max, you always need to consider the maximum value. So QG max is 63 nanocoulombs. So based on that, you understand IG plus would be 63 nano divided by 1 micro, right? So that's going to be 126 milliamp. Okay. Sorry, 2 into 63 nano. Okay. So during turn on, the KVL equation would be something like this, that is VCC minus VCEQ2 minus IGRG, right? So the KVL equation would be something like this. Okay. So you substitute all of that over here, you will get what is RG. Okay. Yeah. So VCEQ2 is also given in your question as 0.2 volts. So this is 0.2. Okay. So 15 minus 0.2 volts minus IGRG, right? So you can compute what is RG from here, right? IG is 126 milliamp. Okay, fine. So whatever you considered as IG plus was this current. You have a gate current something like this, right? So whatever you have considered as IG plus is basically this IG plus. Okay, so this was your first question. That is to compute your gate resistance RG. Okay. So how did we compute that? Just compute what should be IG. If you know what is IG, so IG is basically 2QG by the turn on time. So you know what is IG and you apply KVL over here. So you get what is RG. Okay, simple, right? Just get the gate current and apply KVL, you get the answer. Okay. So a follow-up question for the driver circuit used in question number 10. Which one of the following response is correct? For the same, find the magnitude of V naught across the load resistance RL by considering the high duration of pulse 0.6 ps. Okay, so what should be V pulse and how would you expect V naught to be? Okay, so that's your question. So you can understand that since Q1, right? Since Q1 is a PNP transistor, right? So if you give a high pulse over here, then obviously Q1 would be off. So if your Q1 is off, so you have uh, Q1 is off over here. So this would be a logic low circuit. So um, logic low circuit. So if you have a logic low circuit over here, Q3 is going to be turned on. Okay, so your device VG would be off right now, correct? So you will be having over here when V pulse goes high, let me take another color. When V pulse, so your V pulse is something like this, okay? So when your V pulse goes high, V naught would be something like low, correct? And vice versa, when your V pulse goes low, right? Your V pulse has gone low, therefore your PNP gets forward biased, okay? Your PNP will get forward biased. And then what would happen? Your PNP is forward biased, therefore VCC gets connected to this point. So this would be VCC. If your this point is VCC, then obviously Q2 gets forward biased because you can understand base would be more positive than the emitter. So Q2 would be forward biased. Therefore, you will have a high pulse to VG and your MOSFET S1 is going to turn on. Therefore, when your V pulse is low, your V naught would be high. Okay, so you get a complementary waveform over here. So this is your V naught and um, this is your V naught and this is your V pulse. Okay. So obviously response 2 is correct, right? Response 2 is correct. So again, they have given the question that for the same find the magnitude of V naught across the load resistance RL by considering the high duration of pulse is 0.6 TS. So you assume that the pulse is coming for 0.6 TS duty interval, right? So this is basically 0.6 TS if this is TS. Okay. So what would be the average output voltage then? So when the device is on for 0.6 intervals, so you have 48 volts over here and the device, so 48 volts is over here and you turn on the device for 60% of the duration, right? So it would be 48, 0, 48, 0, 48, 0, something like this, correct? So if you average it out, you can understand that you're going to have a voltage of 48 into D, right? If you average it out. So 48 into, okay, so over here the pulses for 0.6 period. So obviously you have a complementary relation. So if your pulses for 0.6 period, the MOSFET would be on for 0.4 interval or 40% or D dash interval. So 48 into D dash, so 48 into 0.4. Understood, right? So because we just saw that when pulse is high, the MOSFET is actually off, right? So when pulse is high, S1 is off. Okay. When pulse is low, S1 is on. Okay. So that is why, since they have told that the pulse is high for 60% of the interval, it means that S1 is off for 60% of the interval and obviously S1 is on for 40% of the interval. Okay. Since S1 is on for 40% of the interval, if you average this particular thing out, you will be getting 48 into D dash, right? 48 into 0.4, which is 19.2 volts. And that makes sense, right? You're just averaging it out. Okay. So what is the maximum value of switching frequency that can be used for the MOSFET switch in Q1? Okay. So what is the maximum switching frequency? It's a question. So you understand that the MOSFET is on for only 40%, correct, of the total time interval, right? So with that, they have also given that the minimum on-time duration is 1 microsecond. In the problem, it's mentioned that it is 1 microsecond. So the on-time, minimum on-time is 1 microsecond, and that should be the maximum duration, right? For your TS. Your TS cannot exceed this particular interval, right? So zero point 0.4 TS would be equal to 1 micro, correct? This is basically DTS, okay? So this is basically DTS. So the relation is DTS is being equated to your turn on time, okay? So with that, you get what is TS, right? So TS is basically T on, that is 1 micro, divided by 40% or 0.4. Therefore, you get Fs as 400 kilohertz. Okay. So this is the maximum value of switching frequency you can push. If let's say you 100 of instead of 400 kilohertz, I make it 4 megahertz, right? If I make it 4 megahertz, then what would happen is that TS is what? TS would be 0.25 micro. Okay, 0.25 micro is way less than your 1 micro. Okay, so then what would happen? You're not getting enough time to actually turn on the MOSFET. The MOSFET will not be turned on properly. Get it right? So you need to have a specific period as turn on period. You cannot go below that period for your switching frequency, right? So let's say you want to switch this device at 10 megahertz. You will not be able to switch this device at 10 megahertz because what? Because the turn on period itself is 1 microsecond. So you cannot go below that. Okay. Yeah. So that is why your turn on period will be DTS will be restricted by your the turn on transition duration, which is 1 microsecond over here. Okay. Okay. So the load resistance over here in question 10 is being replaced by an inductive load, which draws 10 ampere current from the input DC source. Calculate the shunt snubber capacitance. Okay. So yeah. So this is what is given. That is okay, so this part was not given anyway, but anyway, so you have an inductive load, and what they have done is it draws 10 ampere current from the input source. So if you have an inductive load, obviously the load is something like this, correct? And it is drawing 10 ampere. Okay, so calculate the shunt number capacitance. So we have already done this kind of a question. So you know that C is going to be what? Sorry, IL into TF by 2 VCC, correct? So you know what is IL? IL is 10 ampere, right? And TF is 74 nanos divided by 2 into VCC is 48. Okay. So it's a straightforward relation, I guess. So you get what is C from this. Okay. Again, it's just a substitution of all the known parameters. Okay. Okay, so the next question is the gate resistance branch connected between A and B in question 1, right? It is replaced by following combination. So instead of a simple gate resistor, you have this surge current providing circuit. Then find the value of capacitor if the turn on and turn off duration are considered the same. So anyway, we have again solved this kind of a problem in the previous set itself, right? So what is the capacitor? So how do you size this capacitor? Um, right. So how do you size this capacitor? You know what is RG1, right? So RG1, we computed it as 117 ohms. So if we go back, right? Yeah. So we computed RG1 as 117 ohms. Okay. So RG1 is 117, right? So yeah, RG1 is 117. By rule of thumb, we generally choose RG2 to be how much? RG2 will be RG1 over 5. Okay. So you know what is RG2 from by knowing what is RG1, and you will obviously know that since your turn on and turn off durations are same about 1 microsecond, you will know that phi tau, right? Phi tau is equal to what? The turn on duration. So tau is equal to R2 into C, that is your 1 microsecond. So from this you compute what is C, right? Okay, again this was a simple problem that is based on the time constant. Okay, so this was one entire set of a problem, right? Wherein we started, I think, over here. Yeah. So first you needed to compute what is RG. Okay. So in the simple base drive circuit, you will know that the first problem was that you know what is IG. So IG is basically 2 into QG divided by T on. T on is 1 microsecond anyway, right? So you know what is IG, and to calculate RG, you just need to use the voltage VA minus VB. So VAB divided by IG. So VA voltage is going to be this voltage can be found out by KVL. So from that, you know what is RG, correct? So this was the first problem to find out RG. Next, they asked, okay, given the base drive circuit, so what is the correct response, right? If your V pulse is something like this, since you have the PNP transistor of Q1, your V naught is going to be completely complementary, and they have given that it is for 0.6 TS, right? So the pulse is 0.6 TS, therefore V naught would be how much? V naught would be simply 0.4 TS, correct? This would be 0.4 TS. Okay. So you can find out that the average would be how much? VCC into D dash, right? D dash is 0.4 over here. This is your average, correct? 48 into 0.4. Then what is the maximum switching frequency? Maximum switching frequency is simply your on period for the device. Okay, on period for the device. So T on for the device, that is 0.4 TS, should be equal to what? The turn on transition, that is 1 microsecond. So 1 microsecond is equal to what? 0.4 TS, right? That will give you the switching frequency. You cannot go above the switching frequency, or else you are going to have the turn on period of the device lesser than the turn on transition period. So with that relation, you found out that this is 400 kilohertz. Then you calculated the Schnumber capacitance, that is C is equal to ILTF by 2 VCC, right? So yeah, so this was this rubber capacitance, and finally you saw this problem that you replaced it from a simple resistor to a kind of a surge current providing circuit. Okay, so then in that scenario, what should we see? So you obviously know that the relation is simply the settling time, that is phi tau should be equal to the turn on period. So you know that R2 by rule of thumb is 1/5 of R1. You already calculated R1 in the first question. So I mean in the first part of the set. So R2 will be R1 by 5, and that would be equal to your period, that is 1 micro. So C is something like this. Okay. Okay, so let me check the question till this point. Any doubt? IG increases or decreases in totem pole. Okay, so IG decreases, so that's why you use that. Okay, so I just drink some water. So let me continue from here. So the next question is, consider a voltage source. VCC is 50 volts, inductor is given, and the MOSFET in series. The inductor carries a continuous current of 1 ampere. The instantaneous voltage across a MOSFET, if it suddenly turns off, right? The total fall time is a sum of turn off, delay, and fall time. Refer to the datasheet for missing parameters. Okay, so um, so first we go to the MOSFET data sheet. There you will find information on the turn on delay time, rise time, the turn off delay time, and the fall time. Okay. So what would be the voltage across a MOSFET? You can assume that the MOSFET would be something like, so you'll be having something like this. I will lump all the inductances to over here because we will have inductances over here, inductances over here, and so on. But anyway, let's lump all the inductances together. That is L. Okay, this is your VDS, right? And they have told that the inductor carries a current of 1 ampere. Okay, so what is the voltage across a MOSFET if it suddenly turns off, right? And the voltage source is VCC is equal to 50 volts is connected, right? So the MOSFET is turning off, right? So then what would happen to the current? What would happen to the switch voltage? So V switch will be then as shown over here, right? So VCC plus LDI by dt. Okay. Why it's a plus LDI by dt? The switch is turning off. Okay. So the current is coming in this direction. So do not get confused that okay, VCC minus LDI by dt. Reason is the device is turning off. Okay. So the device is turning off means what would happen? Basically, there is a di by dt in the negative direction. So where will we? Yeah. So the di by dt is in the negative direction. Okay. So the current is the switch current ID is basically falling. The switch current is basically falling. Okay. So it would be falling like this. So there is a negative di by dt. So di by dt is basically negative. So that's why we have written VCC plus LDI by dt, considering absolute sense. Okay, DIDT is negative actually. Okay, so actually it will be what? VCC minus LDI by dt, that is the actual relation. But since your di by dt is negative, you can write minus L into minus of di by dt absolute value. Okay, that is equal to VCC plus LDA by dt. Okay, this is just the absolute sense. So the total fault time, you can understand that it is going to be the turn off delay time plus the fault time together. So which is 103 nanoseconds. Okay. So the di by dt is what? Di by dt is 1 by 103. Why 1 by? Because the current is 1 ampere. Correct. So current is 1 ampere divided by 103 nanoseconds. Okay. This is in ampere per second. Okay, right. So this is your di by dt. Therefore, your V switch will be what? V switch will be 50, whatever is your VCC plus this particular value. Okay, you can understand that you are going to have your V something like this. Your voltage will not go to 50 directly. Your voltage will not go to 50. It will be having something like this and then it will go to 50. We wanted to find out the peak. So this particular overshoot is due to LDA variety and your DA variety is negative. Therefore, it gets added up to the switch voltage. Okay. Right. So this is again a straightforward question. Again, so what do you do in order to arrest this? You use an RC shunt snubber, right? So that is what is asked. So it uses an RC shunt snubber for protection. So calculate the value of capacitance, the minimum value of resistance, and the maximum value of resistance for this number. So you of course know the calculation by now, back of the hand probably. You know C is equal to what? 2IL, I'm sorry, IL TF by 2 VCC. And you have R between an R minimal, R and then an R maximum, right? So R minimal was based on the phi tau relation that you generally use, right? And R maximum was based on the KVL relation. Okay, so assume that the MOSFET is on for 20 microseconds. Okay, so yeah, so the same thing is shown over here. That is, the R minimal is based on this, and R maximal is based on this. Okay, so you have two paths over here, right? So since VCC is going to appear over here, so you tell that you have that the current through this path I capacitor is equal to what? VCC over R. Okay, right? So that should be based on the rating of your maximal device rating ICM. You can find what is ICM from the device data sheet. Okay, from data sheet you can find what is ICM. Okay, so yeah. So the point is, of course, C is equal to IL into TF by 2 VCC. That can be determined directly. And from the data sheet, you will see actually two ratings. That is the pulse current rating and a continuous current rating. So if I can open the data sheet once, just hang on a second. So if I open the data sheet, yeah, so typically MOSFETs have what is called as a continuous current rating, which is ID 50 amperes, and something called as a pulsed current rating. Okay, you can see over here the pulsed drain current is 200 amperes, right? So the continuous drain current is 50 amperes at 25-degree case temperature, and the pulsed drain current is 200 amperes. That is, it can withstand a pulse for a very short duration of time. Okay, it cannot withstand 200 amps continuous current, obviously, but it can withstand a pulse for a very short duration of time. Okay, see, they have told the pulse width also. Pulse width should be less than 400 microseconds. Okay, if your pulse width is less than 400 microseconds, and of course the duty should be less than 2%, that is 400 microseconds. If there is a pulse of 400 microseconds, now then only after 98 percentage, right, or 98 into 400 microseconds, you will have another 400 microsecond pulse. Okay, so basically it can withstand for 400 microseconds a current of 200 amperes. So we will consider that as a maximum rating for our design. So that is why, um, considering that scenario, we have designed the resistance. So VCC divided by ICM minus IL should be less than R, should be less than T on minimal by phi C. This is something you have learned from the lecture slides itself. So the minimum value for snubber turns out to be 50, which is your VCC, divided by ICM is your pulse current rating, and IL is 1 ampere given the problem. Okay. And similarly for maximum also 20 micro again given in the problem divided by 5 into C, your C is 1.03 nanofarad, right? Again, it's a direct substitution, right? You can understand it's a direct substitution. Okay. Yeah. So calculate the power rating again. So you can understand that if the on time of the MOSFET corresponds to zero point 0.4. Okay. Question number 16. Okay. So what is the power rating? Power rating would be simply half CV square into F. Okay, so that's what you are substituting over here again, right? So F is known and your duty is simply 0.4. So you substitute, you know what is C, right? You know what is VCC and you know what is FS, you get what is PR. Okay, half CV square into FS. Okay, so did you guys understand this particular problem set? That is, first, without this number, you try to find out what is the peak voltage that the device needs to block. So it would be something like this, you know, right? So because of a negative dI by dt, you understood that this will should be blocking a higher voltage, which is VCC plus LDI by dt drop, correct? And the drop is actually negative because DIDT is negative, so you get added up in the switch. So it turned out to be somewhere around 1 kilovolt. So in order to suppress that, you added a number and the value for capacitance of this number and R minimal and R maximal are asked. So again, you will use the pulse current rating, right? So ICM is based on pulse current rating for the device, which is 200 amperes. Okay, and later on, based on that, you will compute what is the C, R minimal and R maximal. And finally, with that, you computed what is the power rating. So the power rating for the resistance is basically it has to dissipate the energy stored in the capacitor, in the snubber capacitor. So half CV square into Fs. Correct. So yeah, so you know all of that, you get what is the power in the resistor. Okay, so this was one problem set. Okay, we will move on to the next last two questions. So overcurrent protection is applied for this MOSFET as shown in the figure below. The diode D0 is a combination with 0.7 volt drop. Calculate the value of drain current for which the circuit operates if Vref is 2 volts. Refer to the data sheet for missing parameters. So the missing parameter is what is RDS. Okay. So again, we have solved something like this in the previous problems as well. So basically, V plus should be more than or equal to V minus for the overcurrent protection to operate. So V plus is what? The voltage over here, that is VD naught plus VDS on should be more than V minus is basically Vref, right? So VD naught plus VDS on is I into RD, ID, RD minus Vref should be more than or equal to 0, right? So from this you can find out what is ID, correct? Okay, so if you go back to the data sheet, we will go back to the data sheet. You can understand that the RD, right? RDS is given as 0.04 ohms. You can go to the, yeah, RDS is given as 0.04 ohms, right? As highlighted over here, correct? So use that information and yeah, so RDS is 0.04 ohms. So then using that information, you can compute what is IDS on. Okay. Right. Okay. So this was about V plus. How do you compute V minus? They have told that Vref is 2 volts. Yeah. So from that you substitute that in this inequality and you will get what is ID. Okay. Okay. So and if that is fine, we will come to the last question for the day. That is, which of the following parameters is true? Gate drive power requirement for MOSFET is more than BJT because the former is a charge control device. Gate drive power requirement for BJT is more than MOSFET because the former is a current control device. Gate drive power requirement is same for both MOSFET and BJT, none of the above. So can anyone try to answer this question? Gate drive requirement for MOSFET is difficult or gate drive requirement for BJT is difficult? Any answers? So which is difficult? Gate drive for MOSFET or gate drive for BJT? Okay, so yeah, so why?
Because it requires
Any idea?
constant current supply to reach
Correct.
by square R.
Correct. So you know that BJT is basically like a current controlled current source. Okay, current controlled current source, that is IC is equal to beta times IB in the saturation region. So a collector current can flow only and only if and only if there is an IB. The moment you withdraw IB, BJT will turn off. Okay, it cannot maintain the collector current, right? And so that's why you need a constant current source at the base. Constant current source is required at base. And whereas you consider an FET or a MOSFET, okay, it is a voltage control voltage source, right? That is voltage control current source, beg your pardon. So the current source or I channel current is given by the transconductance into VGS minus VTH. VGS minus VTH the whole square. So you know that if you maintain VGS, the channel current will flow. Okay. So basically you can have the CGS capacitor getting charged up, right? If you charge up the capacitor, that's enough. I need not have a continuous IG current. I just need an IG current profile, something like this, right? It can go zero during the rest of the periods. I just need a peak IG current to charge up this capacitor. I just need a peak negative IG current to discharge this capacitor. Whereas for this is for a MOS. Whereas for a BJT, you need a base current which is something like this IB on. This is IB plus, and to turn it off, you will have something like this, right? So this is something that's a um, problem. So what you will essentially require is for BJTs, you require current source gate drivers. Current source gate drivers, which are more difficult to implement compared to MOSFETs, which require only voltage source gate drivers. Right? So this is the advantage of MOSFETs, right? So gate drive requirement for BJT is more because it's the current control device. Okay. Yeah. So this sums it up. Any doubt so far? You can write it in the comments section. Sir, how VREF? Yeah, so VREF was given is in the problem itself, right? Yeah. So here itself you can see VREF is 2 volts. Okay. So basically, as I have written over here, you require VD0 plus IDRD minus VREF should be more than 0. That is for the comparator to turn on, right? So you require V plus more than V minus. V plus is over here, that is VD0 plus IDRD should be more than VREF. Okay, so VD0 is 0.7 plus ID into RD is how much? RD is 0.04 ohms. So 0.04 ID minus 2 should be more than or equal to 0. So you solve this, ID will be what? ID is equal to 2 minus 0.7 divided by 0.04. Understood? Yeah. So this is how you do it. Okay, but anyway, they have given the diode is a series combination of two diodes. Okay, so this is not just one diode, it will be two diodes. They have not represented that in the problem. Let me use an eraser. Okay, okay. Just a small correction. So there are two diodes over here. So D naught, there are two. So it will be 2 minus 0.7, again minus 0.7 because there are two diodes. So 2 minus 1.4 divided by 0.04. Yeah, so that is why it is 2 minus 1.4. Yeah, so there are two diodes over here. So two diodes, that is 2 into 0.7. So there are two diodes. That is 2 into 0.7. Okay. So then, yeah. So then in that case, again you solve the inequality, you will get something like this. Okay. Basically V plus more than V minus, or VD naught, which is two diodes, plus IDRD should be more than V reference. Solve this inequality. Solve this inequality to get ID. Okay, so beyond that current, it will trigger. So that's why it's an inequality, right? Beyond that ID, it will trigger. Okay, so is there anything else? Or it's almost 8, we can close for the day. So any other doubts so far? I think we have seen almost all problems in MOSFETs and BJTs and the overcurrent protection and this number as well. We have seen multiple problems, so I think this should be enough for you guys to solve the assignments. Okay.
The waveform of MOSFET.
Sorry?
And
Hello?
from the last question that we had,
Sorry, I'm not able to hear anything. So can you just type? Hello, Akshit. If you can type, like probably I can get your message. Different means like I didn't understand your question. So MOS waveform for the last question, you are telling this one. So the reason is because obviously it's a charge control device, not a current control device. I mean, it's an voltage control device. So you know, right? Like basically MOSFET can be represented something like this. That is including the capacitances, you will be having the CGS capacitor, CGD capacitor, CGS capacitor, and CDS capacitor. This is your gate, source, and drain. So your basic drive is connected to this. So if you tell that the MOSFET is turning on, you tell generally that if VGS more than V threshold, MOSFET turns on, right? That means that the CGS needs to be charged up. Okay. And once you charge up CGS, once you make the CGS let's say you make VGS is equal to whatever is the drive voltage VCC. Okay, drive voltage may be plus 15 volts. Then you have made it plus 15 volts. You need not push any current. A completely charged up capacitor, right? It will hold 15 volts. Why does it need any current further? We have already charged up, right? So that is why once the capacitor is charged up to 15 volt, the charging current will slowly decay to zero. That is why for MOSFETs, you have something like this. Okay. For BJTs, you don't have such a phenomenon. You always need a continuous base current because you know I is equal to beta IB. Your BJT is only as good as the current that you feed at the base. Okay. So that is why we have this is going to zero. Right? You understood, right? Akshit? For MOSFETs, you have the current decaying to zero because it's a capacitor. As completely charged up capacitor doesn't require any current to maintain that voltage, right? It just requires the charging capacitance, nothing more. Okay, charging current, nothing more. Okay, okay. So if there are any more doubts, please go ahead, or else we can close for the day. Okay, so I guess we can close for the day. Thanks everyone for attending. And in the initial stage, of course, the PPT wasn't backed up, so I couldn't start off early. So thanks for hanging out and sorry for that. But anyway, I think we have covered a lot of problems, around 19 problems, and I think they should be enough for you to solve the assignment problems. Okay. Yeah, and all of the problems he has covered, that is BGT drives, MOSFET drives, and the overcurrent protection and the snubber design, right? Different problems we have seen, the calculation of the RC values, right? Basically, it's just some time constant and something related to KVL, KCL. You just know the basics, you can do it. Okay. Yeah, so that's it. Then I will stop sharing and
Yeah.
sorry.
Whether this recording session will be available.
Yeah, it will be uploaded to YouTube, I think. Yeah. You are able to access, right? All the other recordings if you want.
The assignment problems are very complicated to solve. So we
So no, the point is these sessions are supposed to help you guys with that. So I hope it will help. But yeah. Anyway, you go through the lecture slides. You go through the problems and see how it has been solved in the problems. So from that you can try to take a cue. Okay.
had any query, how we can access, whether you can mail you or message you. Is there any
So
contact?
there is a course mail ID, right? In that itself, you can type in. There is a course mail ID, right? I think when you enrolled for the course itself, they would have given some course ID.
No, there is only Google Forms there.
Yeah, Google Group. That's what I was telling. But if you want, like, I can just type it over here. This is my. This is my mail ID. If you want to reach out, you can reach out over here. No worries.
Okay, thank you.
Okay. Okay. So thank you everyone for attending, and yeah, have a great week ahead.